Sure, there's some questions on the midterm. No one have any questions on the midterm? Well, I'll ask you a question. What do you think of it? Yes?
I find it hard to tell exactly how much detail was asked for in the answer. In some cases, it seemed like the shortest answer possible was expected, and in others, it seemed like we were expected to write a considerable amount. And it was really hard to tell exactly what was wanted.
There's the answers to the midterm.
Right.
Yes?
I have one question on the one on the valley line needed stabilization.
Mm-hmm.
And since the thing that I have picked up from the university since I've been here is that valley wines are generally standard quality.
Oh, that's a horrible word. They are competitive priced wines.
And generally their main problem is that they are low in acid. One of their main problems.
Right.
And I would think that the way to stabilize large amounts of valley wines would be with acid ion exchange.
Mm-hmm. But I specify particularly a San Joaquin Valley dry red wine. And I think if you'll recall in lecture, I stressed the fact that that is the type of wine that usually gives the most trouble to tartrate stabilize because it's high in potassium, and it's usually marketed young before there's much diminution of the potassium from deposition of potassium by tartrate. So that generally requires all three treatments. First, refrigeration, followed by filtration, and then ion exchange in the hydrogen form to the extent dictated by taste considerations, and then quite often ion exchange in the sodium form to finally get it to the point where it's stable. So that's why I specified a dry red wine, and I think I stressed that in the lecture. You know, one of the difficulties, as you're all aware of in making up exams, is to try and be absolutely clear in what you're asking for. I've been doing this for a number of years. I never succeeded yet in making all my questions absolutely clear. In fact, if they're understandable, I'm satisfied. Another difficulty that I find in making up exams is to try and ask questions that bring out principles and not these picky-finish questions that are so easy to ask. I'll admit that in the lectures we do cover a great deal of material, and it's difficult to point out one thing as being more important than something else because practically everything we cover in a lecture is of almost equal importance. This used to be a semester course, and now that's a quarter course. I still have to cover practically the same material I did in a semester. So all of you students who have taken the course since it become a quarter course have had to work just that much harder to acquire the same amount of material, or practically the same amount of material that we formerly gave in a semester. But I cut out everything that I figured was non-essential, and we still have a great deal of material that I think is essential. So I try to prepare a fair, evaluative exam and touch on the principles and on the more important parts of the material that's been covered in the lecture. As I say, I've never reached the ideal yet, but I keep trying. Any other questions on the midterm? Well, Dr. Webb and I had a bit of a misunderstanding on the lecture he gave you Monday on protein. I used to try to attempt to cover all that material in one lecture, and I finally gave up several years ago and divided into two lectures. Now I understand he went back Monday and covered the whole thing in one lecture. but he said that he covered some of it very hurriedly and very skimpily. So do you want to devote the rest of this period to discussing the material in the protein lecture, or do you want me to go over it, hitting the high points, or what? Because I feel that in a 50-minute lecture, it's impossible to cover the protein material adequately. So which do you prefer? You want discussion or a re-lecture or what?
Well, could I ask a question to start it out?
Sure.
Yeah, I had one equation on the board. I had force is equal to Q times Q prime over dielectric constant times R squared. And I wasn't quite sure that equation and what it meant, and exactly what the dielectric constant was.
Okay. F equals the force of attraction. Between molecules. In this case, we're talking about protein molecules. And that's delineated by the Q and the Q primed, because they represent the charges on the two molecules. And these charges are separated by a distance r. R standing for any distance that you want to designate. And the dielectric constant is defined by the symbol epsilon. So what this says in effect is that a decrease in epsilon is going to increase the force of attraction. For example, the dielectric constant of water at 20 degrees centigrade as compared with ethyl alcohol is 80, compared with 23. So what the thing says in net effect is that the force of attraction is inversely proportional to the dielectric constant. And the dielectric constant is in turn determined by the liquid and also by the ionic strength of the liquid. The liquid in which the material is in colloidal suspension and the dielectric constant, or the ionic strength of that liquid. So if we go from water with a dielectric constant of 80 and suspend our material in alcohol with a dielectric constant of 23, then we're going to greatly decrease the solubility of that protein because the force of attraction is going to be greatly increased. Is that explained?
Would you say that once again?
If we go from water with a dielectric constant of 80 to alcohol with a dielectric constant of 23, first we're dividing by 80, then we're dividing by 23. So we have decreased the dielectric constant, we have increased the force of attraction because we have decreased the number that we are dividing by. And that's one of the reasons why it's advisable to blend before stabilizing because you can also change the alcoholic content, and sometimes if you have a solution that is right on the verge of precipitating, a fairly small change in alcohol content with a consequent change in the dielectric constant and in the force of attraction between these molecules is going to result in a clouding and a precipitation. Any other questions?
Why don't you go ahead and hit the most important points?
Okay. You're all familiar with the three types of binding. That is why the three types of which the polypeptide chains are bound together. I'm sure that was mentioned. The three types of cross linkages, the diethyl bridges formed by the cysteine molecules. The salt bridges, that's formed by free carboxyl groups from the amino acids, and the free amino groups from the amino acids. It's a just a result of the Coulombic attraction. Between the free carboxyl groups and the free amino groups. And of course the hydrogen bonding. Now the hydrogen bonding is very important. It's a very weak bond, but there are so many hydrogen bonds between these peptides that it is one of the strongest forces holding the peptide linkages, or holding the peptides in a certain given form. And the diethyl linkage, of course, is the SS linkage. Another thing I'd like to emphasize is that these protein molecules are large. They're very large. Large enough so that there are effective boundaries between the particles and the solvent. And this is a very important property of the proteins, that they are large enough that there's an effective boundary between the particle and the solvent. And of course, as you know, the proteins are amphoteric. And as I'm sure all of you know, the term means they have both acidic and basic properties. And at the isoelectric point, these plus and minus charges are balanced, and the protein molecule as a whole is neutral. In other words, it will not move in a charged field, or a charge will not move it, because they contain an equal number of basic and acidic charges. And each protein has a definite pH at which it's in an isoelectric state. So every protein, and this is another very important property of these proteins as far as the effect on stability is concerned, has a definite pH at which the charge on the protein is neutral. Yes?
Can this change a lot though?
It can change by pH changes. And that's another one of the reasons why it's advisable to make blends prior to the time that you're going to stabilize, because you can be quite a distance from the isoelectric point, make a blend, and move very close to the isoelectric point, where before you add a stable solution as far as protein is concerned, when you approach the isoelectric point, the molecules are completely neutral if they're at the exact isoelectric point, or nearly so if they're very near it. They no longer repel each other. But you think of these particles now, if one of these is mainly positively charged, another one mainly negatively, if these two are positively charged or negatively charged, they're going to repel each other because they have the same charge. If you change the pH to the point where the isoelectric point is reached and they are negatively neutral, that is, the molecule as a whole is negatively neutral, then they can approach each other, and then you can get interaction between the plus charges here and the minus charge here, and so on. So that's why the isoelectric pH is very important as far as the protein stability is concerned. And it will shift from the addition of salts. That's one of the easy ways of doing it. And of course, by changing the dielectric constant of the medium. Yes?
Since the isoelectric point seems to be kind of critical. Doesn't that mean that most of the protein is all the same? Most of the protein in the solution is all the same protein? And if that's the case, what protein is it? Or what types of proteins are they?
There are globular proteins. We have characterized them by molecular weight, and according to our results, the molecular weight ranges from 18 to about 27,000. The pH range of the isolectic pH range of the proteins that we've worked with, that we have characterized, is quite narrow.
What is that range?
All the way from 3.4 to about 3.8. Now, if you have your proteins in an acid solution, then the net charge is positive. In other words, the protein has a net positive charge. And of course, an alkaline solution has a net negative charge. So as you move towards the acid side of the pH scale, you're going to increase the positive charge on the protein molecule, or going the other way, you're going to increase the negative charge. And this is due, of course, to the suppression of part of the positive or the negative charges as you move from one area of the pH range to the other. Is this all clear so far? Well, as precipitation of the proteins has to go through two steps. To get them to precipitate, first they must be denatured. So denaturation, and the second step, of course, is flocculation. As long as the protein remains unaltered in its native state, it is very, very difficult to cause it to flocculate or precipitate. It must be partially or completely denatured before it's susceptible to changes in visible appearance. Because the denaturation of proteins always results in their losing some of their original solubility. Now, the protein can be denatured by a number of things. And after denaturation, if the denaturing agent is removed, suppose you heat a wine. That's one of the denaturing operations. Then you remove the heat and cool the wine back down to the original temperature again. Your proteins can do one of two things. They have been partially denatured. Some of the bonds that hold the polypeptide chains together will have been ruptured. And when the denaturing agent is removed, then these reactive sites are going to seek each other, and new bonds will be formed between the polypeptide chains. So depending upon the extent of the denaturation, it can refold. And think of the protein molecule as a bunch of chains just hooked together by numerous bonds. And when you denature the thing, you break it and open up one or more of these rings. Just think of them as rings, an easy way to visualize it. You remove the denaturing agent, whatever it happens to be, and then these chains will start to refold. Bonds will reestablish between the chains again. And it, depending upon the extent of the denaturation, it can refold to almost the original form. In that case, the solubility of the protein is not altered measurably. It can refold to a different form, say appreciably different from the original form. In that case, the solubility of the protein is appreciably lessened. Or it can refold in an entirely different form. In that case, the solubility of the protein is nil. So it depends upon the extent of the denaturation and the way that the bonds reform between the polypeptide chains as to whether or not you have changed the solubility of the protein in solution. And of course there are a number of things that can cause denaturation. Heat I've already mentioned. Shaking. Just shaking a wine can, under certain conditions, cause denaturation. Ultraviolet light is probably the strongest denaturing agent to which we could expose wine.
What was that?
Ultraviolet light, UV light. Ultrasonic waves will also do it. Of course, there's acid, bases, organic solvents, salts of heavy metals, detergents, and I want to stress detergents. Because I have known of actual cases where wines that were protein stable by the usual tests, after they were bottled, became protein unstable because they had not done a good job of rinsing out the detergent from the bottling equipment. And quite a bit of the wine that went through during the first 20 to 30 minutes later on folded, became protein unstable because it picked up detergents. Now, why would you think shaking would cause denaturation? What happens when you shake? Form foam, don't you? And the protein film will form or extend over these air bubbles. And that's your foam, of course. And then the protein is subject to surface denaturation. And the net result is the unfolding of the surface peptide chains. And you're exposing reactive sites, and you're not going to get the same refolding action that you had previous to the formation of the foam. So we've known of a number of cases where excessive foaming during bottling has resulted in the wine becoming protein unstable, where it is protein stable by the usual test prior to bottling, just from excessive foaming. And by the way, the Muscat varieties are probably the worst foamers that we have in bottling or in any operation that subjects the wine to agitation. As I say, UV is the strongest denaturing agent that we know of, because around 270 nanometers the radiation at that wavelength is absorbed mainly by the aromatic rings. In other words, the three aromatic amino acids that are present in the protein molecule: tyrosine, phenylalanine, and tryptophan. And the net result of this UV radiation, that is at around 270 nanometers, is that the peptide bonds next to the aromatic rings, are split, and you've disrupted the chain. In other words, the aromatic ring absorbs strongly at 270, and the net result is that the peptide bond hooking the aromatic amino acid to the rest of the chain is split, and you got a disruption of the chain, and you have exposed sites, active sites for reaction. And to the best of our knowledge, the ultraviolet rays or light breaks bonds that are not touched by heat denaturation. So actually, if you expose a bottle of wine to ultraviolet light, you're having two effects. You're going to have a heating effect due to the fact that the temperature of the wine is going to increase some from the absorption of the rays of the sun, but the greatest effect is going to be due to the absorption of the ultraviolet spectrum at around 270. And you'll break bonds that heat alone will not touch. Now the ultrasonic waves, they act by several methods. Now, of course, you're all familiar with ultrasonic, quite commonly used in laboratories for one thing, for mixing and for cleaning and so on. You get mechanical action. You also have thermal action. And the last one is production of oxygen from water. So ultrasonic can have the three effects: mechanical action, thermal action, and producing oxygen from water. Then they get into the aromatic amino acids that get it from the ultrasonic waves. Now, mineral acids and alkalis will cleave the salt bridges, which is one of the three methods of linking these polypeptide chains together. And I mentioned detergents as a possible cause, in fact a noted cause in a number of cases of protein denaturation. This applies to the anionic detergents because they can combine with proteins when the proteins are in an acid solution. Of course, in wine they're in an acid solution. Because in an acid solution the proteins have a net positive charge, and the positive charges on the protein molecule can react with the negative charges on the anionic detergents and combine, and you get denaturation. In fact, one of the standard methods of precipitating proteins is to react them with trichloroacetic acid. In fact, we developed a method in my laboratory here a number of years ago for a quick analysis of protein stability by adding trichloroacetic acid, heating for 10 minutes, and then measuring the nephelis before and after heating. That's just because the positive charges on the protein molecule react with the negative trichloroacetic acid anion. So to sum up on denaturation, you can have proteins practically completely denatured with no visible change taking place in the solution. So you can have white wines that have the proteins practically completely denatured, and you can have no visible change taking place in the wine. But the net result of denaturation is always eventually a decrease in solubility, and depending upon the degree of the denaturation, it can lead to visible changes and eventually to flocculation and precipitation. Now, flocculation. The solubility of these proteins in water or water ethanol, speaking of wine or speaking of a water ethanol solution, depends upon the temperature, pH, dielectric constant, and the ionic strength. I discussed this formula right at the start of the class. Now, I've discussed the effect of the isoelectric point, the fact that the proteins are least soluble at the isoelectric point. But I also mentioned the fact that changes in ionic strength can have a decided effect upon the protein solubility. In fact, under certain conditions, a change of only 0.01 to 0.02 can render a wine which is formerly protein stable definitely protein unstable. And of course, you change the ionic strength by adding salts, acids, and so on.
Question, what's the difference between changing the ionic strength of the solution and changing the pH?
You can change the ionic strength just by the addition of salts, which have practically no effect upon the pH change. Whereas you could change the pH a great deal and have very little effect upon the dielectric constant. That's why you have to keep them separate. Now I'd like to go over the highlights of the precipitation of proteins by combination with other substances. Remember that if you have the proteins on the acid side, they're going to have an excess of positive charges on it, so they're going to combine with certain organic acids and will form insoluble precipitates. So certain organic acids, such as trichloroacetic acid, will result in protein precipitation. And the amount that's combined is generally equivalent to the number of amino groups that are present. Now, if you have a solution in which the net charge is negative, in other words, most of the charges are negative because it's on the negative side of the isoelectric point, then they'll combine firmly with certain metals, iron, copper, for example, and will form insoluble precipitates. And if you're having a precipitation of positively charged metals, copper and iron, with negatively charged sites on the protein molecule, then the effect of the metals, principally copper and iron, is greater the greater the atomic weight and the greater the number of charges that are on the ion. So, iron with 3 versus copper with 2, iron would be more reactive than copper. And of course, the atomic weight also is a factor. But the one thing that you must remember, and I'd like to stress at this point, is that even though your protein molecule may have a net positive charge, it still has negative sites available for reaction. And if it has a net negative charge, it still has positive sites available for reaction. Yes?
What's a soluble precipitate?
Pardon?
What's a soluble precipitate?
A soluble precipitate? If I use that term, my tongue got twisted. Which happens. Now, I really want to stress this point because I don't think in any wine are you ever going to have all of the sites on the protein molecule either positive, and it's essentially not going to have them negative because your wines never run that high in pH. Therefore, you're always in danger of reaction with both cations and anions, in other words, with heavy metals or with certain organic acids. That's why anions and cations both must be considered a danger at all times, because you have both positive and negative sites available on the protein molecule for reaction. I mentioned the fact that when you denature a protein, you split the bonds between the polypeptide chains to a greater or less extent, open them up, And that way you expose a great number of active sites to anything that wants to attack them. As long as your molecule is intact, with the bonds not broken, then the only sites that are available for action when anything is floating around in your liquid here will be any reactive sites that are exposed on the surface of the molecule. And think of the molecule as a ball. In fact, the molecules in wines are globular proteins, so they're more or less ball-shaped. But once you start breaking these bonds here, causing these things to unfold, then you're exposing more and more reactive sites. And that's why denaturation has such a terrific effect upon the solubility of the protein in solution. But again, I want to emphasize, yes?
Yes, are denatured proteins have a higher ionic strength than the ones that are not denatured?
Have a higher,
Ionic strength.
only if they're broken up into individual particles. Again, I want to emphasize that you can have a great disruption of these bonds and a great unfolding of the chain without any visible changes in appearance. In other words, flocculation will not occur unless there are flocculants that are available for the reaction between the reactive sites and the flocculating matter. That's why you can have a perfectly clear solution, a perfectly clear wine. You have ionic reactants present. You denature the molecule to a certain extent, and all of a sudden the wine will cloud on you and perhaps eventually precipitate. One thing that's of interest is that in addition to salt bridges and dithiol linkages and peptide linkages, or linkages between the peptides, I should say hydrogen bonding, dipole-dipole bonds. Under certain conditions can be a very, very strong force affecting the action of these proteins in solution. And of course, as you all know, the dipole-dipole bonds are between polar non-ionic groups like OH, SH, NH2, and so on. They're very weak. Compared with salt-like bonds, they're very weak. But, as I said, in certain conditions, they can exert a stronger binding action than the salt-like bonds or the hydrogen bonds because there are so many OH groups that are available in the protein molecule. And the reason I bring this up is because it's long been known that with high sugar wines, the coagulation of proteins is very difficult to achieve. In other words, if a sweet dessert wines, you can subject them to a great deal of heat, denaturation. You're breaking the bonds, but the dipole-dipole bonds that form between the hydroxyls on the sugar molecule and some of the other groups on the protein molecule, even though the molecule may be more or less denatured, are so strong that they will remain in solution and will not flocculate and coagulate. And of course there are protective colloids, naturally occurring protective colloids, and you can also get protection to a certain extent from the addition of gelatin, and at one time, in fact, still used to some extent, agar-agar or gum arabic have been used and are still used to some extent to provide protein stability because they will act as protective colloids and prevent the coagulation and precipitation of the proteins. Yes?
Do you ever get a cloud that is just protein? Or is it always combined with something else when you get clouding?
I can't imagine a protein cloud in wine being entirely protein. It's going to be a combination of protein, protein tannin, protein metals, and perhaps even some protein anions, protein acids.
For that reason, is that why in champagne when you have yeast autolysis, you don't get a protein cloud? Something else to it.
We have done a fair amount of work on the change in protein content of wines before and after fermentation. And we have always found that the autolysis of yeast results in a release of nucleotides and not proteins. Because at one time we thought that there was a big increase in the protein content, and by later refining our analytical techniques we found out that there was a big increase in the nucleotide content rather than protein content. So I don't think it'll be a problem in champagne. Any other questions? Well, in wine, your protein content, of course, ranges over quite a wide range, anywhere from 2 to 100 parts per million. 100 parts per million is very high. That'd be a brand new wine. And it's only a small part of the total nitrogen content that's present. But as I stressed before, protein clouding in white wines is probably one of the biggest stability problems one has with white wines, with the possible exception of browning or oxidation. In fact, I'd rate those as the two major stability problems in wines. And all wine has been the scene of a protein precipitation. And as soon as you crush the grapes, you can start reactions going with the proteins. The reactions continue during the fermentation and after the fermentation. So at any given moment in the life of this wine, a certain amount of protein precipitation has taken place, a certain amount of protein denaturation has taken place, and at any given moment in the wine, you're going to have a certain protein level and a certain state in which the protein is, or a certain average state in which the protein is present. In other words, any given moment in the life of the wine, that wine has reached a state of equilibrium at that point. At that point, it is precipitated all it can under those particular conditions. But anything that can disturb the state of equilibrium is going to start another precipitation. Or, if you push it the other way, it's going to increase the chances of non-precipitation. Now, since we want our wines as protein stable as possible, our objective is to push this equilibrium point. Now, unless you entirely remove all of the protein, that wine, with a given wine, it's possible, as long as there's protein there, for protein precipitation to occur. So you can never say that a wine is completely and finally stable, because you always have some protein there. And if the conditions, the equilibrium conditions, are pushed too far in the wrong direction, then you're going to start precipitation again. So what you try to do is to push the equilibrium conditions as far as possible in the desired direction, and to establish the wine in such condition that during the life of that wine, protein precipitation will not occur. So to attain this equilibrium, one of the first things that one to think of to do is reduce the amount of the reactants. And of course, protein is the primary reactant. And this reaction is also subject to the law of mass action, and if you reduce the amount of reactants, then you're going to push the equilibrium in the desired direction. So you reduce the protein content by one of several methods. One of the most common ones is heat. More desirable, of course, is the use of bentonite. And you follow both operations by refrigerating and filtering. Potassium ferrosiodine Q-fix will also remove protein, though usually bentonite is more effective. And occasionally we find wines which seem to be impossible to stabilize, that is protein stabilized, by bentonite fining. Then we have two choices. Three if we want to use heat, but preferably not use heat. We can add bentonite to wine at a temperature of 45 degrees Fahrenheit, or approximately 45 degrees Fahrenheit. Maintain at that temperature while the lees settle, and then filter. This is a difficult operation because at that low temperature, the bentonite does not settle out very well, and it makes a difficult filtration job. Though it often will clean up a wine, stabilize a wine that will not stabilize by fining with bentonite at the usual cellar temperature. The other way is to first fine with Q-fix, or preferably potassium ferrocyanide, though that of course is illegal. But fine with Q-fix, and then after the Q-fix is mixed well into the wine, immediately add 2 to 4 pounds of bentonite, and then let that settle. And quite often that will stabilize a wine which could not be stabilized by straight bentonite fining. And to maintain equilibrium in the wine, it's necessary to keep the effect of the disturbing factors at a minimum, and those things that can disturb the equilibrium are numerous. Tannin, acids, metals, detergents, foaming, aeration, heat, cold, blending, filtration, ultraviolet light, practically anything you do to a wine. So that's why it's recommended that you do as many things to the wine as you are planning on doing prior to the time that you stabilize for protein, because so many things that you can do to the wine afterwards can disturb that equilibrium. In other words, you shouldn't add tannin or acids after you've attained protein stability. Of course, you want to avoid metal pickup. Be sure all detergents are rinsed from your bottling equipment. You use a type of bottling equipment that minimizes foaming, and if you do get foaming, slow down. If it's a vacuum filler, slow down the or decrease the vacuum, which will minimize the foaming, and avoid aeration. And also warm storage conditions, because even elevated storage conditions, which you could not call actually heating the wine, can over a long period of time also result in some denaturation. And of course you should blend before you stabilize, because change in pH, protein content, tannin content, alcohol contents, ionic strength, all can affect the protein stability. And lastly, filtration. It can remove protective colloids. And if your wine has a appreciable amount of protective colloids, when it goes to the bottling, you give the final polish filtration, sometimes you can remove enough protective colloids to render the wine protein unstable in the bottle. That's why you need a tight filtration at the end of the stabilization cycle, so that you remove the greater part of these protective colloids and not remove them at the time that you give the wine a polish filtration. And if you have a choice on bottles, stay off the white and green bottles, because they'll transmit the UV rays, or I should say, it won't screen them out. Brown bottles are much more preferable, and of course the ultimate in protection from glass is red. I don't know if anyone's using red bottles. And lastly, the total protein content is a very poor index of stability, because we found by our research work that it's the type of protein that's present that is a principal factor, provided there's a minimum amount of protein present. Therefore, total protein content is a poor index of wine stability. And final, the lower the pH of the wine, the more apt that wine is to be protein stable. We found that wines that have a natural pH of 2.8 to 3.1 are almost invariably protein stable without a thing being done to them. Any questions? That's it.